second half, where we'll try to make things more interesting. But you had a full 2 minutes to digest whatever incoherent thing I said before, so you can ask questions about that first. Okay, good. So there is a very nice write-up of this Chigger-Simon story for you on Gage-Field in a nice paper of Graham, Dan Fried, and Greg Moore. I think that's almost unique coordinates where you can actually read about it in a way that's understandable to a physicist even. Okay, so now we've just talked about just the theories. We actually see that in physics we like to think about continuous fields. We like to play with continuous fields because once things become not continuous, we have no idea what to do, or our training doesn't allow us to think about it in a way that we have. And what I've just demonstrated for you is that if I want to think about discrete groups and their actions and the topological operators associated with them, we can use continuous fields to think about it in this BF theory that I've just defined for you. So now let's see whether we can get more, whether there are other things that we can learn. So I'll consider an action which is more interesting. So this is a theory that I studied with Enoch and Tom in various occasions, where it will be two BF theories that are interacting in some interesting way. And this will have a lot of nice physics to talk about. So we'll consider an action which is in 5 dimensions, 2 pi I times we have m. We'll have n times b wedge dc. And then, so this is going to be a 2 form. So this is a 2 form. I will put a label of a 2 form to clarify. And then I will add another term. Let's call it 2 times n times a 1 form, 3 form. Right. So just this theory by itself, this here gives me a Zn times a Zn gauge symmetry, 1 form gauge symmetry. This one here is going to give me a Z2n 0 form symmetry times a Z2n 2 form symmetry. Okay. And on this side, as we've just discussed, we have the operators of my theory. I have a WC, which is exponential of pi I integral of of C. Then I have WB exponential of 2 pi I integral of B and gamma and gamma prime. Similarly here, right, we have, so here, I guess I should be, this is of some gamma of 2 dimensional closed space. So the analysis that we just talked about for BF theory, it didn't matter what this dimension is. We can actually work it. It's always going to be the same. So this is a vector. So I have an observable, which, let me use different letters. Let me call it V, acting on some sigma A acting on sigma 1, which would be exponential of 2 pi I integral on sigma 1 of the holonomy this, and then we have the C3 on some sigma 3 exponential 2 pi I integral on sigma 3 of C3. Okay. so far, these two theories, they don't talk to each other. And this one generates for us a Zn one form global symmetry and a Zn one form global symmetry. These are Zn one form global symmetry. Okay.
Why did you I'm confused by the use of the word gauge and global symmetry. You said gauge symmetry in the.
It's both. There's both things are at play. So this is, as we discussed before, this is a genuine gauge symmetry, right? But then these are topological operators, right? So this is a topological operator, which is Zn valued. So it's a topological operator associated to a Zn one form global symmetry. And this is a topological operator, which is a Zn one form global symmetry.
Shouldn't that be a two-form global symmetry?
In 5 dimensions. No, one form because it measures a two-dimensional. No, sorry, it might be it might be a 3 form. I cannot count. Don't trust my counting.
These are two-dimensional.
Yeah, that's right. That's right. That's right.
Yeah, all right. So
Yeah, that's right. It might be a two. I can't count.
okay.
Don't trust my counting. But there's a Zn and a Zn.
The operators are two-dimensional. Okay.
Yeah, the charge operator is a two-dimensional. Right, because the form of the symmetry is the degree of the charge operator. The charge operator is a two-dimensional. So that's right. So this is I should call this a 2. Similarly here, this is a holonomy for the A1 field. It's a topological operator. It has a charge operator associated to it. The charge operator are these guys, right? And this one act on charge operators, which are these guys. So here you also have some Z2n symmetry and a Z2n symmetry. And let's see if I can count properly. So this is a 1D object. The charge object are 3 dimensions. So it's a 3 form, right? This is a 3D, the charge of 1D, so this is a 1 form. Good. So this theory, right? So here, this is a product of 2 theories, and then I have these So the key point to know over here, each one of these elements is of course invertible, right? If I raise any one of them, if I raise these to n, they become 1. So these are all invertible operators, and here these are all invertible operators. So then the question is, we can use this to think about certainly topological operators for invertible operators. Can we think about non-invertible operators? Can we say non-invertible operators? From the point of view of this action, I can add an interaction term, which I'm going to write as 1 over 2n times. I'm going to write it in this way. I will introduce some fictitious fields, phi1 minus 2n times a wedged e of some is 0, and then some beta minus n is b. Okay, so this is an interaction term. So the reason why I'm adding these modes is because I want to construct an action that is gauge invariant. So I've introduced phi and beta, which are going to be non-dynamical fields, right? They're non-dynamical because I noticed that the gauge transformation for A, the local gauge transformation for A, corresponds to a shift symmetry for phi. Similar to the question that was asked earlier, okay? And here, beta, the local transformation for B corresponds to the shift symmetry for beta. And these things I'm adding so that what they effectively do is that I know from the starting point that this theory has U1 fields, but the dynamical part is much smaller. It's a Zn times Zn. So I'm free to add these fields as I want, as long as they don't change. They don't project out to Zn fields, right? So the parts that are removed by these terms is already projected out by this action, meaning the continuous part of the theory. So now when I add this interaction, right, I have this Zn times Zn gauge group and this Z2n times Z2n gauge group, which are now talking to each other in a non-trivial way. So you could ask, what happens to these operators now? Okay. So if I look at, for example, so now I can think about the equation of motion for this system here. If I look at the equation of motion, let's say for the field, if I look at the equation of motion, for example, for A1 over here, I would get an equation which would be 2n d of C3 minus d beta minus n b squared is 0. Okay, so what this equation tells us is that if I look at now this operator here, which I constructed beforehand, it's not an operator that is topological anymore, because of this equation of motion, if I take sigma 3 and I deform it a little bit, right? The reason why this was topological before is when I deform sigma 3 by a small amount, there's a change which corresponds to the integral of C3 on some manifold, which was the bordism of sigma 3 and some sigma 3 prime. And because DC3 was 0 originally, so that was topological. But now, so let me say that more clearly. Before there, the reason why that was topological is if I take the space sigma 3 here, and then suppose I deform sigma 3 to some other sigma 3 prime. What I would like to say is that independent of any deformation here that I have, that this operator is going to be trivial, but and that simply followed from the fact that I can write the change as coming from an integral of dc3 inside this volume, and this was closed, so this was 0. Okay? But this is no longer true once I add this interaction term. So because this is no longer true once I add this interaction term, I need to modify this operator in some way so that I can, if I want to keep that operator to be an operator of the theory, I could ask, does it survive? What happens to it? Does it need some modification? If so, how? Okay. Whatever this modification has to be, it has to be consistent with the fact that now the new equation for the C3 potential is 2n dC3 is modified by this. Okay. Any questions? Good. So the answer to try to construct this is that I want to construct now an operator. Can
I ask something actually?
What?
Because you're arguing that is not topological by looking to the equation of motion.
Mhm.
But like, shouldn't we look to the gauge transformation of C to argue that is not gauge invariant anymore?
Yes, so those are equivalent in the sense that the thing that I'm actually keeping track of is the Gauss constraint. So before the Gauss constraint was dC3, and now it's this. I didn't want to talk about Gauss constraint anymore. It's just an accident of the fact that this is a first order system that I can think about those together in this way. Yeah, but you're completely correct. Okay, good. So I need to modify this operator in some way. So when I write this expression here, I can, in fact, because this beta was just a pure gauge, the quantity that I want to look at is 2n VC3 minus, I'll write n squared b squared. So this is the equation that I want to look at. I can set beta to 0 because it's just a gauge degrees of freedom. But the key point here now, if I try to construct an operator, which is something that looks like the holonomy of C3, I simply cannot do that because you might ask that I want to undo this. If I try to integrate it into some v, I have to hit it with a c derivative. But this quantity as given is not a quantity that I can pull a derivative out. But this quantity is indeed closed. And the reason why it is closed is because our B fields, the fluxes for B fields are trivial. So this is a closed object, but I cannot simply pull a D out because this is something that lives in a non-trivial class. So what the thing that I can do, which is the statement that I can do about this is to say that suppose I construct my VC operator, which acts on some sigma 3, and sigma 3 is a boundary of some other manifold. Okay. Then the statement that I could say is that the evaluation of V on sigma 3 has to be consistent with the evaluation of this operator on this manifold. Okay. And what that tells me is that VC3 evaluated in sigma 3, I can make it consistent by having it give me an answer, which is 1 over 2 n times integral of b squared on m. Right? So this is a condition that I can impose, which is simply telling me that whatever is the operator that I define on sigma 3, it's experiencing some inflow from the bulk. Okay? And that inflow from the bulk is exactly the piece that needs to that has to account for this fact, which accounts for the interaction with the bulk. So how can I construct such an action? The answer is the following, is that if VC3 defined on this surface sigma 3, I can do it by introducing some what physicists would call statistical field on sigma 3. And I look at the exponential of 2 pi I of C3 plus a term which I will write as being N A D A plus A wedge B.
Sorry, on the equation just above where you're writing,
Yeah.
you mean to write the variation, and you wrote the formula for VC3, the B squared, but
The statement is that when I evaluate the VC3 on sigma, which is a boundary, it should give me the anomaly term in the bulk.
oh, I see. Okay, yes.
So here I have sigma 3, and then I have m in the bulk.
I see.
So
Okay.
that is a condition that I can impose, which satisfies which is consistent. Okay. So the claim is now this operator does it. Okay. And what this operator does is that here what you have is a Chern-Simons theory that is coupled to the bulk with this to the bulk with this B field. Okay. And in this action, if I evaluate this integral explicitly, if I evaluate this on some sigma 3, with sigma 3 being a boundary of something, you can explicitly check it indeed reproduces that. So this operator, now when I add this sort of interaction term, is what replaces this operator.
I'm a little bit confused about what you said earlier.Maybe I misunderstood what you meant, but you were saying something along the lines of B squared is closed but not exact. And I'm a little confused as to exactly what you mean by that, because do we not have a relationship between DC3 and B squared that lets us, or are we not imposing these equations of motion?
Good. So this is again a subtlety of talking about U1 versus ZN classes, right? So the technical thing that should appear here is the Pontryagin square of the class. What B squared is, because remember B is a discrete. It lives in a Zn. I'm taking a Zn element and treating it as a U1, right? And the lesson from the first lecture was precisely that, right? The naive differential equations is not enough. I need to think about the fact that these can live in non-trivial cohomology groups with discrete coefficients. Okay, so I cannot simply say that, but I can say this. And indeed, when it is trivial, then everything comes in. So in this example, the key point to demonstrate here is that when I started with this discrete gauge group, which I described using this U1 gauge field, remembering from the first lecture the fact that these are actually the pieces that survive in evaluating this action is the terms that are non-trivial in H with Zn coefficients. When I add this interaction term also have to be consistent with that. Okay. And what it tells you is that the consistent operator, the topological operator that you get is this thing, not that thing. So then you can ask what types of fusion rule this operator should generate for you. Okay. Any questions about? Go ahead.
I probably asked this earlier, but was the coefficient of this interaction term quantized, or can it be arbitrary?
No, it cannot be arbitrary. It's constrained by looking at the Gauss constraint and making sure that the theory is Gauge invariant. That's right. So yes. So I put 1/2 here because this is the amount. This is a specific example that appears when I'm studying SUN super Yang-Mills theory. This is a SIM-TFT for that, right? That associated the global form, and this coefficient have to be quantized in a suitable way, but I didn't want to have to talk about it. Okay. So if I change these numbers, this will change. That's a good question. Go ahead.
Yeah. Can you, instead of considering this Chern-Simons term, just use the rule above? So like the operator would be like the exponential of C3 plus the integral over m of B squared.
Good. So good. So you could say that, maybe I should just write that always. But the statement is that I want to define an operator from which I can evaluate on any cycle, not just ones that are boundaries of something. Right. Written in this way, this is a statement of saying that, you know, if you evaluate on a boundary, then it should go. Then when you integrate by parts to some m, it should cancel that term, and that's why I have this thing. Another way to say the statement more correctly is that when I insert this operator, right, because of this interaction term, it breaks the Gauge invariance. This is the statement in a very particular way, and the way you can understand that breaking of the Gauge invariance is that you always have an anomaly inflow on the operator, so you need to decorate it in some way. And what this decoration is doing is that it's saying that you're taking the Chern-Simons theory on this three-dimensional operator, and this Chern-Simons theory has this one-form symmetry, and you're taking the global one-form symmetry of the Chern-Simons theory, and you're identifying it with this one-form symmetry in the bulk. So this is what this coupling does. This coupling tells me that it's identifying this Chern-Simons, the global symmetry of this Chern-Simons theory with the gauge symmetry in the bulk, right, via inflow. And that's why you needed this interaction. So that's a more physical way of explaining why.
Are there other inflow terms you could have chosen instead of this, and this is just a particularly simple one? Or
Good.
is this somehow like
This is the simplest one that I could pick. In principle, so what the lesson here is that this operator, if I want to cancel this effect, I need to add something to absorb the anomaly, I can stack it with any theory that I want, right? The Chern-Simons one is the simplest one, but the issue is that you can pick a more complicated theory, but then there will just be some operators that live on the surface that don't talk to the bulk at all, right? So this is an example that sort of projects out a lot of those. Actually,
So it's like the nature of the coupling between the.
right? Go ahead.
Maybe a stupid question. Is this what physicists mean when they talk we are stacking a lower dimensional TQFT and
right.
coupling it?
That's right.
Ah, nice.
This is exactly an example of that. So if you heard of those words, this is an explicit realization of that picture, right? We have you have an anomaly coming from the bulk because of this term, or you can understand it from this point of view, and you want to cancel it, right? So you couple you take a TQFT on the defect, which is non-trivial, and then you couple it to the bulk to cancel the anomaly. So this is the stacking.
This might be a stupid question, but why is that an anomaly?
Why is it an anomaly? It's an anomaly for this, let me see, which symmetry? This one. So in presence of the operator, this symmetry is anomalous.
Right, in the presence of this beta operator, that symmetry is anomalous.
That in presence of this operator, this symmetry, this gauge symmetry, is broken, right? But from the point of view of this Chern-Simon theory on the defect, this one form symmetry, sorry, it's not this one, it is this one, right? In presence of this Chern-Simon theory on the defect itself have this symmetry, this one form or two form symmetry to be consistent, right? But that two form symmetry had an anomaly. Self anomaly, and that self anomaly is what I'm canceling, what I'm identifying with the anomaly coming from the bulk by the stacking and do it. So more precisely, what I'm doing is I have the Chern-Simon theory. What I'm doing is that in the bulk, I have this Zn two-form symmetry, which in the presence of the defect is broken, right? And then I can measure by how badly it is broken. And how badly it is broken is actually measured by this term, this phase here, right? Then I can say, what I can do is think about all hope is not lost. I can take the defect, but then I'm going to add something dynamical on the defect, right? Which have itself some Zn symmetry, and that Zn symmetry with the right anomaly, right, to cancel this thing.
So the claim is that, so in the presence of these presence of this operator, the Zn gauge symmetry is broken, right? So that the Zn, so that's Zn1 and that's not Zn2 then. So if there's a Zn1 gauge symmetry which comes from B, that's broken.
Yeah, you're right.
Okay, great.
I can't count. I told you.
Yeah, that's right. So I just trying to get this straight in my head. Thank you so much. Yeah.
Yeah, I cannot count. Another way to see that, it has to be the one form symmetry, because on the thing that needs to be canceled on the defect is a one form symmetry which acts on the Wilson lines of the Chern-Simon theory. It's a one form symmetry that needs. Yeah, good. So this is what physicists mean when they say stacking, right? So you invent something on the defect that have the right anomaly to cancel the bulk. Okay. And it's a necessary thing in order to have a well-defined topological operator. Okay. So if I can't do this, then I cannot have a well-defined topological operator. So what is now the upshot of this is that okay, so this point we understood. Then you could ask.
So to fix this anomaly that you pointed out, you sort of proposed this formula for this operator, and you explained that we could think about this stacking with a lower dimensional T. Is there some way to not? Is there a sort of axiomatic way to say, okay, there is an anomaly, therefore there is a TQFT that captures that anomaly, rather than sort of proposing it and defining that?
Well, in a sense, that's what I said. You said that whatever this operator is, there is an anomaly that has to be canceled. Right. This is what this term means.
I guess my question is that always the case that the way that you encode that is by some lower dimensional TQFT?
That is one way that I know of how to do.
There's not a theorem or a result that says it is always such.
It's a good old physics thing. We mess around and find out. It's you make an observation that this thing is there's an anomaly inflow that you have to cancel. But we also understand from many other physics principles that whenever you have an anomaly inflow, what it suggests is that you have modes there. So if your question is that is the statement that the presence of an anomaly inflow and a defect, the statement that you must have something dynamical on there, that statement is correct. But what do you put there? That is related to the question before, right? In principle, you can put anything there to cancel, right? So you want to try to add, you want to have some notion of minimality, which is a tricky thing to think about. You want to just say that what is the smallest set of things that I can put such that I can cancel this anomaly. But smallest, of course, is a hard thing to define, right? So here is an example where I can just turn on a U1 level n Chern-Simon theory, level 2n Chern-Simon theories on the defect, and that is enough to completely absorb the anomaly, right? But then that have to interact with the bulk. So that theory that lives on the defect interact with the bulk via this way, and that's how it does cancel this, right? So you no longer have a one-form symmetry that lives on the defect global symmetry that lives on the separate from the one-form gauge symmetry. You have a single gauge symmetry, which becomes a one-form symmetry on the defect. So you've identified those. Okay. Okay. So the statement now, once I have defined these operators, I can ask, suppose I take some V on some sigma 3. So before we saw that when I take this operator and raise it to the nth power, I get identity. So this was an invertible operator. You can ask, is it true here? Right. So you can take V times C3, and then you can multiply it with VC3 and ask what you get. That this gives you something that you can think about. So this is a path integral over two choices of this A field, dA and dA prime, times exponential, get 2 pi I of sigma 3. In particular, put a dagger here, so that would be the orientation reversal of the operator. Okay. Okay. So this is going to be this, which will give me C3 minus C3 coming from either two choices of the two. But then the second term, which is 2 pi I, integral on sigma 3, you get n times A dA minus A prime dA prime. Okay. For the sake of argument here, we can take n to be 2. Right? You can take n to be 2 because otherwise the dagger in general doesn't make this invert this. Plus A minus A prime wedge B. Okay. So this integral evaluate by having a new set of fields in this path integral. You can do a linear transformation where you say this is now alpha, and then you can define an alpha prime, which is A plus A prime here. So you can try to evaluate this thing. Then this term will cancel, And then you get path integral of d of alpha prime, d alpha, and exponential, if I can do this right, by I integral of sigma 3 with an n times the easy one. So you get alpha wedge b, and then here we have a is going to be alpha plus alpha prime, and b is alpha minus alpha prime with a 2. Get here plus alpha prime over 2 wedge d alpha plus alpha prime over 2 minus so you get the original theory, that I should keep track of, is n times alpha wedge d of alpha wedge b. And then I should have cancellations. Minus and alpha prime. Yeah. If I multiply two of these theories of this kind, this is what I should get. I have a minus. There's a mistake. Come to see the mistake. You know, you've done this calculation.
I can't keep track of signs, but I can keep track of factors of 2. I know you missed the factor of 2 in the Chern-Simons term when you defined it.
Do you remember the answer? Just give me the answer. We should get b of alpha prime times the path integral of something which is just n times alpha prime d alpha prime. And then you have another piece, which should be d. No, good. So this is alpha prime alpha plus another term, which would be alpha d alpha plus alpha wedge b. Is that correct? The point that I want to get at is, I apologize, I don't have the exact answer, is that when I try to integrate out, when I try to evaluate this integral, what I get is an integral on 2 variables of alpha and alpha prime, and then only one of the alphas that's coupled with b. If the answer is done properly, what you should find, this is up to an exercise, what you should find is that the integrating the alpha prime term should localize to flat connections of alpha. So it localizes to some flat connections of alpha. And then the answer, once you do it properly, I'll leave it to an exercise, you should get some sum over choices of integrals of b itself on some 2-dimensional surfaces sigma 2 where sigma 2 is an element of H2 on sigma 3. You should get an answer of this kind. Which is, I promise you, it's an exercise that if you sit down 10 minutes, you can do it carefully. So why is this interesting? So this is interesting because what it's telling me now, if I take the operator V and I multiply it with its Hermitian conjugate, which is an orientation reversal, I do not get 1. I get something which is a condensation defect. Right?
Is that H2 with Z mod n coefficients or?
Yeah, it's H2 with Z mod n coefficients. Right, it's on sigma 3. Right. So when you, so the presence of this modification that you have to do on the operator, right? What it tells you is that if I take now this operator and multiply it with its Hermitian conjugate, I should find that you get a condensation defect. So ignoring me fumbling this computation, let me write down what the answer should be. So V times V dagger is going to be proportional up to some coefficients. So the reason why I was trying to do this is because the coefficient itself is actually important. So let me write it. You get some coefficient which is multiplied with this thing, which is sigma 2, which is a sigma 3 times the n of E to the 2 pi I of B sigma 2. Here. And you do get a coefficient here, and this coefficient is not going to be simply a number, right? This coefficient is going to be itself some TQFT coefficient. It's not going to be 1. It's not going to be some number. It's going to be a TQFT coefficient associated to one of these choices of the fields. Right? So this A is also some non-trivial quantity. It's A of sigma 3, but it does not talk to the bulk. Right? It's a coefficient which only depends on sigma 3 and the variables which I integrate over. It's a TQFT coefficient. And then you get some operator here, and this operator here is a condensation defect. Okay. So I'll leave this to an exercise, and I'm happy to talk about it later if anybody wants to work through it carefully. Okay.
Is it allowed to set n equals 1? If these discussions, why not?
Well,
there you would have an infinite sum. That's why I'm asking.
So it's not a U. So n equal to 1. We argued before the BF theory had no degree of freedom. I started with. That's why. So n equal to 1. Here when I started, then all of these operators are trivial.
I agree.
Right. So the lowest level one where you should get something interesting is n equal to 2.
Even if those were all trivial, I grant, then you could still do this deformation where you add these other terms. I mean, I'm not asking whether it would be interesting or not. I'm just asking, is it possible? I mean, is there some?
Yeah, you can evaluate. You evaluate, but everything is 1. All of the operators would be 1. In particular, here you get a condensation, right? Yeah. You can just, and then if n is 1, then this is 1. There is no, this operator that doesn't exist. That's all. I mean, you can formally put 1, but then you just get 1. So you need to do at least n equal to 2 to see that you get something non-trivial. So, okay, good. So the statement now is that the thing that I wish to demonstrate here is by using this Lagrangian method, you can start to see how you can actually start to recover the aspects of categorical symmetries that we care about. And in particular, you don't just get some fusion rule, which gives you operators, which are condensation. You can get, so this is not the only operator that becomes non-invertible, but you also start to capture things that you should expect to have, which is these TQFT coefficients, okay? So then you can go and start to look at it. So you can ask which operators become non-invertible when you start adding this sort of interactions term. So we know that this one becomes non-invertible. This one, this operator here, because it's coming from looking at the holonomy of A, and that's associated to looking at equation motion of C3. C3 doesn't appear in the interaction. You will still get the constraint dA1 is 0. This operator stays invertible. And then here you can look at these other operators. Because B2 appears over here in this action, you can look at the equation of motion of B2, right? Then the operator that involves the holonomy of C also becomes non-invertible. And you can check this. And this would be a two-dimensional operator that becomes non-invertible. Similarly, this one stays invertible, okay? So then you start to have a stratification where at the top level, you have 3D operators that are non-invertible that multiply to a condensation defect, which talks to these operators. And then you can go further down where you have two-dimensional operators that become non-invertible. And when you evaluate this one, you actually find it talks to both this operator and also this operator. Okay. So in this way, just by starting with this sort of a Lagrangian construction, you can start to explore, at least from a physics principle, what these categorical symmetries should look like and how they should, what sort of fusion rules they get, and how to understand them from some broader physical perspective. Go ahead.
So apart from giving you that exact equation of motion, do the non-dynamical fields phi and beta have any other purpose?
Yes. So for example, if I add if I take my space-time and I add a boundary, these fields phi and beta can be stuck on the boundary, something called singleton boundary modes, right? So they're going to be related to some boundary modes that live there. And that's so my notes had discussed that in some detail, which I will not be able to get to. But the other thing that I also wanted to discuss, which I won't get to, is that now from this 5-dimensional theory, what you will end up constructing is going to be some stratification of set of topological operators. Some are invertible and some are non-invertible. But then you can ask, how does it act on a field theory at a boundary? So then you can study the problem of taking now some 4-dimensional boundary. And on this 4-dimensional boundary, you can couple some quantum field theory. In this case, the canonical one we can study is some SUN super Yang-Mills theory. And then in the bulk, you have this sandwich picture that we seen get drawn in other places. Okay. So this construction that we have here completely constructs all the different operators of my system, right? So then you can think about this super Yang-Mills theory and the various operators that lives on it. For example, this super Yang-Mills theory can have both Wilson lines and also 't Hooft lines. Okay. And we started by saying that we have SU and super Yang-Mills. So what we should actually always write is the algebra SUN. Okay. And in particular, you have to pick some choice of a global form, right, to give me a proper group, proper gauge group. One choice is, for example, you do actual SUN, and the other choice is you can do P SUN. Okay. depending which one of these choices that you pick, they will correspond to some boundary condition for this theory on the defect. The choice of a boundary condition is what's going to allow you to pick which one of these groups that you want to work with. Okay, and in particular, what you find is that because now the bulk theory is completely solved, you know all the different operators, you can consider operators, one of these extended operators that go from one boundary to the other. So this is a Dirichlet boundary, where I pick which defines my group action. And then in the bulk, you can ask what are the set of things that link with it. Okay, so you have some operators so if you pick one of these that go in the boundary, that depends on the choice of the boundary condition, and then you have the orthogonal set which can link with it. And that you can compute because you know what the solution is. And in doing so, you can completely now solve the problem of understanding when you get Wilson lines or 't Hooft lines, what is the action of the symmetry on those operators. So you can explicitly start to realize this Dan picture because you've completely solved the bulk TQFT via using this action. So this was going to be the next topic of discussion, but I don't have another hour.
You can have like 5 or 10 more minutes. I think we started a bit late, so you want 5 more minutes.
Okay, I can say more, but I think what's more useful is to take questions. That's 5.
Questions?
So how do you see the supersymmetry in this 5D SimTFT?
Oh, good. The 5D SimTFT does not care about supersymmetry.
Oh, I see. So that's purely
That's a boundary theory.
an artifact of the 4D boundary. Okay.
Well, I won't go. It's the definition of the 4D boundary, right?
Right,
Like, good. I'm glad you asked that question because when we do this sort of a construction, what we have is some TQFT in the bulk that acts on the boundary theory, right? The boundary theory could be anything. The only constraint is that boundary theory have to have the symmetry properties that you want, right? And then once it admits some of that symmetry properties, and analyzing the bulk is going to tell you how it acts. It's exactly like we think about representation theory, right?
Right. But if you were to suppose also write down a SimTFT for supersymmetry, how would you do that?
Oh, that's a separate question, which we can talk separate. It's I'm not aware yet of an example of a SimTFT for supersymmetry. But here in this discussion, these are all internal symmetries. So they commute with spacetime. So they commute with any supersymmetry.
Okay.
Ask before that you can also couple a different 3D TFT to cancel this anomaly. Is it clear that the operators will be the same? So, how are the two TFTs related? Because they should somehow be related if they give me the same operator, right?
So I mean, it could be a different TFT that you put in. The question that you should ask: does the action on the boundary field theory care? And that shouldn't care. So you're saying that these operators have a sector that just doesn't talk to anything. But that's fine. Right, the trick is always knowing how to pull those things out. But that's right.
There's a step in the derivation that's dividing a gauge field by 2, and it's not always a well-defined thing.
Yeah, that's right. So here, certainly if so if I take n to be even, everything is fine. But for other values of n, we can work it out carefully. So if you're curious, what you want is that the transformation of this gauge field has a matrix that has determinant 1, and this you can always work out. That's what you want to preserve the quantization condition, to make sure that you're mapping U1s to U1s, not U1s to something else. You just want the determinant of the transformation to be 1.
Find a Zn or Z2n perhaps matrix.
Yeah.
We determine one that's congruent to.
Yeah. So this you can do.
I see.
This you can do. And although I fumbled this thing here, promise you. If you more questions?
There are also open surface operators, right? Like because you have this beta,
Yes.
you can construct an open surface operator of B.
Yeah.
What role do they play in this?
So open surface meaning, sorry, with the boundary.
In the bulk,
Yeah.
take some open surface. You can think of integral of B over the open surface, but insert a line of beta along the boundary of that surface.
Yes.
That's
Yeah.
a well-defined operator in this theory.
Yeah. That is a well-defined operator in the TQFT. You can think about it.
Just asking what role does it play in any of this?
You mean, can I understand it as doing something particular? Like, for example, if I take the open surface and tap it on the boundary. That's what you mean.
I was thinking of completely being in the bulk. I'm not thinking of any boundary in the manifold.
Yeah, so the operator that you want exists, but it's just a statement that the TQFT has many operators in this story, right? In fact, one question that you could ask is that here we have this stratification where we can give you the 3D operators, 2D operators, and the 1D operators. There's a good question to ask: how does this whole thing form a good TQFT? How does it behave? If I try to act this whole symmetry on the boundary, I should expect some fusion category. How do I recover that full fusion category, which is a highly non-trivial question? But that involves actually going on and figuring out all the different operators and all of their fusion rules. This is ongoing analysis, right? And this you can do. And the whole point of this is that because I have the theory and I can completely solve it, you can actually sit down and just enumerate all possible operators and work out all the different fusion rules by using these field theory methods, right? And then you can ask, do I get what mathematicians tell me I should get? Okay, and that's, ask Enoch in the end of the summer. He will give you the answer. Okay.
Not David has an organization. Not.
Well, first, let's thank Ibou again for